Yeah. Yeah.
Okay, our next speaker is Vitto about 2D heterostructures. We're getting shifted by 10 minutes around, and I hope that's all right.
Thanks a lot for the chairman's introduction, and hello everybody again. As yesterday we took a time travel, we supposedly went through the history of the discovery of graphene, both theoretically and experimentally, and we found that graphene, starting from a non-relativistic picture, people can get at low energy, the relativistic dispersion of a direct fermion. And we also found that graphene is gapless. And then the question is how to find a gapped two-dimensional material that is TMD, that we'll go through later. And we know that already in graphene there is a very high mobility. For example, when people found a good substrate to host graphene, the mobility can go up to 1 million, even higher. So the system became ballistic throughout a lateral size of 20 or even larger micrometers. So this is a very good platform. Imagine that if we cool down this kind of two-dimensional electron gas direct fermions with this high mobility and under some certain magnetic field, of course we'll obtain some famed quantum Hall insulator. So that's today. I'm going to start with this section, and later we'll do some little calculation and then obtain that how the Landau level looks like in graphene. And then I will go through a bit more about, since we already have graphene heterostructures introduced yesterday, there will be even more complicated graphene heterostructures and the other two-dimensional materials. So the whole door is now opened by the invention of graphene placed on BM from the very beginning. So we have a tremendous opportunities to study this kind of heterostructures by playing the stacking order and the twisting angle, a lot of things to study. So first, let's go to see what is the Hall effect. I guess everyone knows that, and the traditional conventional Hall effect is discovered more than a century ago by Sir Edwin Hall. And when he was studying a very thin slab of metal, he found that if you apply a vertical magnetic field, and accidentally he measured this transversal voltage, and he obtained some voltage, which is supposedly there is no current flowing, but there is only a voltage proportionally to the applied vertical magnetic field. That's the very famous Hall effect. So if we write this a very easy Ohm's law over there, conductivity should be proportional to current over this electrical field, and then the current density can be written as a carrier density times electron charge and the velocity. And of course, there is a balance between Lorentz force and the electrical force, so we get V dot V equals to the denominator. And then if we plug some little thing which is h long constant in this formula, we will see that the whole thing looks like some kind of quantum physics. There is no purely classic. If you just plug h in the denominator and this denominator, you will get something written as nu times e squared over h. And the nu is later on defined as a filling fraction, and this can be written as h over e, a quantum flux, and b over n, that is the magnetic field shared by each number of carriers. So field per carrier as this kind of thing as a measure. With this, we'll go to the next slide. Classical Hall effect, if we increase the magnetic field B, the whole signal is going through the origin and linearly goes up. And the behavior is very simple. And even this simple behavior is very practically used in our daily base. So we can find Hall sensors in many applications, even nowadays. And this is a very important effect in physics. And in 1980s, early 80s, Professor von Plitzing was doing his experiments using, I think, the silicon 2-day quantum Waals in the National High Magnetic Field Lab of Grenoble. And what he did was he just placed this high mobility two-dimensional electron gas. It's not the 2D materials, but just the quantum wells. And with this sample cooled down at very low temperature and the high magnetic field, he found that the behavior of Hall effect is departing from the linear dependence, and there are some oscillations starting at a finite magnetic field in Rxx, which is blue color. Rxx means longitudinal, the usual way when we do the measurement. And if you measure this transverse voltage, then there will be plateaus correspondingly with each minimum of rho xx, you will have a plateau showing up in rho xy. So this is the first ever topological electronic phase discovered in human history experimentally. At that time, there's no whatsoever topological physics, anything related to that, so nobody understood at the very beginning. And the experiment was done, the first paper was published like 1980, and even very short amount of time, just 5 years later, this phenomenon was won the Nobel Prize very rapidly. So people found that actually those plateaus, if you plot rho xy instead of kilo ohms, you use the unit we showed in the previous slide, which is h over e squared or e squared over h, depending on you plot the resistance or the conductivity. Then those plateaus are actually quantized proportionally to an integer filling fraction times h over e squared. And this thing, e squared over h, is in a unit of resistance of 25 kilo ohms, 812.807572. Well defined, 10 digits. So imagine this has nothing to do any of the sample size, sample quality. As long as you have a good enough sample, as long as if you have a high enough magnetic field, you measure the sample wherever you measure it. Whoever runs the experiments, you always get 1/1 billion precision of the plateau. So that's very beautiful and a very precise phenomenon people found in mathematical physics. It's now already 40 years ago, but people are still very fond of that. So imagine this experiment. People need a high magnetic field and low temperature for something. For example, theoreticians found that if you couple these kind of H channels, we draw this thing in the conventional Hall effect as a skipping orbital already moving in the bulk. Actually, in the quantum Hall regime, classically you can draw a similar picture that every electron is circling by themselves, which is localized. At the edge, there's some skipping orbitals go like that. It's a very classical picture, but this is the very, very first easy way to understand this phenomenon. And we can know that. So after this, shortly after this discovery of integer quantum product, we saw that the plateaus equals to e squared over h and times a constant. A few years later, people discovered that when you even increase even higher magnetic field, those filling fractions can be fractional, and that has nothing to do with this single particle picture. You have to explain everything by interactions. There's a whole set of complicated theory, Lawson states, and other explanation for that. And then this fractional quantum Hall effect also won a Nobel Prize in 1998. So this phenomenon is very fascinating, and theoreticians studied this one, opened a new door, and there's another one related, not directly, but somehow related to topological states, the Nobel Prize of 2016 on this condensed matter physics. So we can imagine maybe there's possibly in the future another 1 or 2 Nobel Prizes should be given to quantum anomalous Hall effect, which means instead of using the very high magnetic field, this quantization can happen at zero fields. That's a very, very useful application because you get rid of any kind of magnetic coils. Without any field, you will obtain a quantized plateau. So that will be very useful for constructing such as superconducting topological quantum computers, etc. And if we go through all the materials people can imagine, can found in our hands, there is only a few ones which you can have quantum Hall effect. For example, we have quantum wells. That's classically studied in many systems, like zinc oxide, and gallium arsenide, and aluminum gallium arsenide, etc. And in this lecture, we are going to review the van der Waals materials. So, as we said, to have this beautiful phenomenon, which might be useful in the future, we have to have a crystal which is layered 2 dimensions first, and then a high mobility, high enough that we can see this quantum oscillation and Hall plateaus at a finite magnetic field people can obtain. You know, the highest static magnetic field in the world is about 45 Tesla. And for the pulsed ones, people can obtain above 100. That's another story. For static ones, if you want to put your sample there, study all these physical properties, the maximum we can obtain is 45 Tesla. Okay, so that's the highest one we can obtain so far. And for these materials, there are already black phosphor ring, tellurine, and TNDs. Some of the TNDs, graphene, bismuth thin. Recently, there is a paper showing that very thin bismuth can also show quantum Hall effect, and also indium selenide, black arsenate, thin black arsenate. Also, there is a recently discovered compound called bismuth oxide selenide 2-to-1 phase. This is also a very, let's say, very high mobility semiconductor in VDW family. And we also have, as I already mentioned in TMDs, have 2 examples which show the very good quantum Hall effect of MOS2 and tungsten diselenide. All right, so these are the material base. So if you look into this quantized sigma xy, the formula, actually it looks very similar to the Gauss-Bonnet formula, which we use to count the holes of a geometric surface. So if there is one hole, there is one integer number added of the surface, and the formula is actually an integral of curvature in the whole surface. So this looks very similar to our case of quantum Hall, that you have some kind of f function, and there's a whole integral of this, for example, the k space. So this thing is actually related to various curvature. Something is a quasi, let's say, magnetic field in the system. And it can be real ones, external ones you apply. It can be also internal ones from SOC coupling, for example. And that's how people construct this system using topologies later on without the real magnetic field. So by this kind of a very simple introduction, I would remind you that this quantum Hall phenomenon is so beautiful that there's a poem which can be quoted here, that this is real phenomenon that we see the universe through a piece of sand. For example, if you grab kind of 2D layered compounds, for example, graphite, you exfoliate them into very thin limit, you do some nanofabrication, then you run an experiment at some condition of low temperature in high magnetic field, you obtain some constant of Planck constant over the elementary charge square. So this is very beautiful that you can do, for example, quantum metrics. Why quantum metrics is important? Because everyone, for example, the kilograms, the meters, seconds, all the units we are using nowadays, you have to define them. So in the past, how do people calibrate their system? For example, for a kilogram, you have to come to Paris each 1 or 2 years to compare with them, and then you go home and the system even degrades itself. So it's not quantum, it's not well defined. So now the SI unit committee decided that all the SI unit has to be quantum. This is why this quantum matrix is important for us, as we already say that the Blitzing constant, which is the h over square, there is a 10 digits precision already. And there's also quantum computing possible using this H channel. For example, if you couple to superconductivity, I guess Benjamin Sesefy already introduced you. There might be some paraphernons in the system existing. So this is the quantum matrix conference held on Paris. I'm not sure where it's Paris, probably in 2019. There's the Nobel Prize winner, Professor William Phillips. What he said is a new kilogram in 2019 is the biggest revolution in metrology since the French Revolution. All these units, kilogram, ampere, mole, and Kelvin, have been redefined using the constants. And using this very conventional setup, people can already have quantum resistance standard. But all these, we need a high magnetic field and low temperature. So for real applications, to save, say, the room of the facility and to make all these measurements easier, we want to have something better at room temperature, better at zero magnetic field. So that's something people have been dreaming ever since the first discovery of quantum Hall effect. After 40 years, nobody has ever achieved that. Probably, you theoretician guys can have some ideas of what kind of new system can we do. Basically is to, for example, have topologically non-trivial systems at higher temperature, or have topologically trivial systems like the quantum Hall at higher temperature and lower magnetic field. The previous one, topologically non-trivial, is already zero field. That's a great achievement. And with all this little background, let's now come to the case of graphene. Okay, the graphene is the number level in graphene. I have to go through this formulas for you. Theoreticians may omit that, but experimentists can have a look. So we said yesterday the Hamiltonian of this direct fermion has no sigma z. So if you write there h bar f as a prefactor, you have a kx sigma x plus y. Tau z is the spin up and down, and then there's a sigma y. You use a simple replacement of vector potential to plug into this Hamiltonian and use a Landau gauge.
Sorry, maybe you can switch the marker so it will be better.
Oh, yes, sorry. So it's not very clear, this one. Let's try another one. No, not either.
The first one after the point.
The one on the front.
That one? Great. It's very good. And this is the Landau gauge, and then we will have to define another x tilde equals to h over dp ky. With these several formulas, we can rewrite this Hamiltonian into there's magnet. So then we have the very well-defined magnetic length of LB, which is h square root h bar over EB. And this Hamiltonian will go to h bar VF. So plus and minus tau z is tilde LB squared. So this is already very simple that we can see that by some simple replacement, the element in the Hamiltonian already looks like a ladder operator for harmonic oscillators. So then we just define another wave function. Is 2. AN and BN for is the two wave function prefactors. Then we'll get wave function returns to the eigenenergy like that. So we already have a prefactor of square root of 2n. Just by solving this formula, we will get at the end En equals 2 plus minus. So So that's the basic formula for these graphene number levels. You can see that it depends on the square root of n, and it comes from the fact that this graphene is a direct Fermi. It's very different from the conventional ones, which we have, for example, there's free charges. We have linear ones. Simply because it's just a harmonic oscillator h bar times omega c. It's the eigenenergy for that. So the graphene one has the square root dependence. And if we say, for example, make an energy difference between two number levels, the largest one we can obtain in graphene is between the 0th and the first number level. And if we run the numbers with this system, for example, for 40 Tesla, then we just replace the n equals 1 minus 0. It will be 1 in the very beginning, and h bar v and over lv. We simply obtain some 20-ish. 20-something millieV for graphene. Forget about temperature broadening or anything. It will give us the largest number level spacing between all kinds of two-dimensional systems you can have already. So that means if you place a goodly length graphene under a field of 40 Tesla, of course some low temperatures, you should have seen the quantization of number levels of IXY. And that's what people did. They ran experiments under 42 or 45, I don't remember the exact number. And indeed, people see a very small wiggling. At low temperature, you have sigma xy in the form of ladder, and then at room temperature, people got something like very shallow plateau. So that's something people can obtain in graphene at room temperature. But imagine you have 40 Tesla, and you have only one place in Tallahassee, probably higher than 42. And that's not very practical for any kind of useful applications. But that's already the best system we can find in the Earth. So let's say we have to, for example, if we need something which has quantizations, H channels at lower magnetic field and higher temperature, we really need to think hard to either change this formula of these number levels, or to have a completely new system which has a larger level spacing. And that's something we need to understand. And this is how it works experimentally. So the experiment was done very early, in 2005. There were 2 papers back to back. Both are in Nature. So we can see that the 0th number level graphene is crossing there, and there's some ladders coming up, and here is plotted in sigma xy. And one important thing for graphene is that this delta axis, which is a subscriptive has oscillation, has something to do with this with another factor which is defined by Bayer space. So what people do is, if you plot the 1 over b, which is this variable, and the number index, which is for each SCH you have a 1 line, and then you just extrapolate this intercept of y-axis and x-axis, and the intercept is about 0.5, which means the Bayer space in monolayer graphene is about pi. And the back-to-back paper from Gan's group, also that previous one was from Columbia University Philip Kin's group. This one is from Gan's group. So they did exactly the same experiment, and they obtained also the shift of 1 over 2 from the plot of 1 over b, and the n is the Landau index. So the index, you just count these plateaus from each Philip fraction. And we can see that actually, unlike this conventional two-dimensional electron gas, the lattice quantum Hall plateau doesn't go to 0. Instead, it splits into 1/2 and -1/2. So that's also a property related to the Bayer space of graphene. And for bilayers, it's different. It doesn't also go through 0, but it splits these two plateaus from -1 to +1, and then 2, 3, 4 of all this degeneracy lifted there. So these are actually at the end one can see that for monolith graphene, the sigma xy is defined by this formula. For bilayer, is defined by that one. Notice that bilayer n equal to 0 is not available, but actually it's eightfold degeneracy for the 0th number level. Okay, so with this little background, we'll coming back later because in our experimental setup, we managed actually to find some system which can make the graphene electron velocity even higher than the original form due to interactions. We'll come back to that later. But with this introduction, let's go back to yesterday's phenomenon of heterostructures. We already saw that graphene can be placed on HBN, and then this system can be expanded to any kind of two-dimensional materials, thousands of choices. So there's one thing that people also found at this similar age, that if you have, for example, we are talking about graphene again, because whenever you talk about two-dimensional system, inevitably you have to focus on graphene first and then expand to later system. So for graphene and HBN, there is something interesting. BN has a lattice mismatch, compared to graphene, is about 1.8%. And this very little difference of lattice mismatch can give us some very puzzling results at the very beginning. So sometimes if you do your heterostructure, you measure graphene and HBN, you will not even only see the central direct peak. Sometimes you see some side peaks. So at the very beginning, people thought it's some kind of impurity or inhomogeneity or any kind of things. People, didn't understand that. And then there were some early studies from STM guys. They run experiments, and if you go to the very simple model, you can see that actually if you twist graphene and HBN or any kind of two-dimensional sheets with a little bit atomic mismatch, you will see that except for this original lattice constant, there was some rotating and shrinking, enlarging lattices showing up as which is defined as a Moiré superlattice. So the Moiré superlattice is the name of Moiré is a fabric, some kind of fabric. I think it originated from France. So when people doing these fabrics, they just ship them because they have a lattice constant. They ship them and they saw that kind of superlattice showing up, and that kind of feature is defined as Moiré. And Moiré is then first time used in two-dimensional system because it's now all surface. It can really define a new potential due to the formation of Moiré, which cannot be really pronounced enough in other dimensionality like 3D or 1D. So actually, quasi 1D can do the similar stuff, but the real one can't. And this is how it looks like. The Moiré wavelength can change in the specific system of graphene HBN from 15 nanometer to about very short wavelength. And it's also characterized by STM studies. So the first paper was from Leroy's group in 2012, and what they did is they have a graphene placed on HBN, and they managed to find the sample under the STM setup with the tip, and then they scanned the morphology, found that with different twisting angle, which is defined as phi, with a mismatch between the two materials, which is defined as delta. Delta is equal to 1.8%, and then you will have a lambda, which is a black curve, changing from 0 point something to 12 or 14, maximum less than 14 nanometers. So this is great because you have a new set of lattice constants, which is way larger than either graphene or HBN lattice constant, and that was not really available before. So, and there is also a rotation between the emergent Moiré lattice and the original lattice, which is defined as by the angle of theta. The tangent of theta is written in that formula. So it's now known, and Leroy and his colleagues did also STM studies. And they found that except for this minimum of density of state at the direct point, you have also other minimums at higher energy, which means if you move your Fermi level away from the direct point, you have another minimum up and down. Some asymmetry also was found by the STM studies. So it's 2012, and no transport evidence has been carried out before that time. And the experiments really soon after that found that indeed there should be some, features showing up of transport evidence. As we saw that the previous slides, the side peak of graphene in resistance or connectivities actually are not artifact, they are real. They can be tuned by rotating the angle between graphene and HBM substrate. If you place this system into a vertical, perpendicularly applied magnetic field, you'll have even more complicated structures showing up, which is called a Hofstadter butterfly. And it's named after the Hofstadter's paper in 1968, so a long time ago. And people found that if you have a super unit, and then all this unit area can have a phi naught, and which can be defined by phi over phi naught, and then the filling of electrons can be defined with n over n naught. Then you have a plot. People call it strand plot or Diophantine plot, whatever you name it. But this is a very beautiful feature that by just plotting this phi over phi naught and n over n naught, every slope corresponding to a Chern number, which is the filling fraction, for example. You have side peaks and major peaks, and it's actually the hierarchy of the side peaks sometimes are a little bit different from the major fan, sometimes are similar, so depending on samples. So that's a simple relation of how the T and S are defined in this diagram. And in 2013, people first time found that this twist thing can create a Morgan superpotential. And at that time, graphene twisted system is already studied many times in theory, but people couldn't have made the first sample of twist graphene yet. And let's see, there were some kind of models trying to solve this problem, because when you twist the system, each unit cell has more than 1,000, maybe 10,000 atoms. DFT calculation is becoming really difficult, so people developed some continuum model. Koshino had a famous PRB paper. He was not the first one to use the continuum model, but he calculated in very detail the system of graphene on BM. He compared the tight binding model with this continuum model, which are in great agreement, and they even find the difference of gap sizes from hole side to electron side. That's how people obtain in transport. You have a higher resistance peak on the left-hand side and compared to the right-hand side peak, so which corresponding to a very weak gap. Yes, please.
How did they make like tight binding model for the Moray? It's like a huge one.
Actually, I don't know the detail, but I guess it's a huge Hamiltonian, and you just run it numerically by force.
So it's in principle, it's very complicated compared to the Moray tight binding. That's that's the reason why they make continuum model.
Yes. Continuum model, they took some approximations, and then the whole calculation, the computational power you need is much less compared to tight binding, and also the precision is pretty good. And so far, people can take also the heterostructure terms into that, and everything works beautifully so far. Then let's see again some experimental phenomenon. So why at the very beginning, sometimes you measure your graphene on BM, you obtain some very weird side peaks that you didn't want at the beginning? It's because there is a very funny effect called superlubricity effect. When you place a graphene on top of HBM or other 2D materials, many of them, there's a bunch of theoretical paper and experimental paper studying that. The surfaces between them, even though they are coupled through van der Waals force, but they are, however, they were kind of, they can slide easily due to this superlubricity effect. And also, when it's commensurate with this lattice of each other, there is some maximum possibility and a minimum possibility of twisting the two layers. So that's why sometimes you have a sample not aligned. If you anneal or heat up the sample, it jumps by itself and it finds itself to a position which it feels more comfortable, energetically favorable, so it becomes aligned at the end. For example, this PRL paper in 2016 did some statistics. It says that as long as you have an angle starting from close to 0 or close to 30, they tend to switch into the value. So, for example, 27, 28, if you heat it up, the sample will become 30. a few degrees also. So imagine that this can happen experimentally. That's how the moire was ever discovered at the very beginning. This is for HBN and graphene. And later, people found that also you can do the experiment in situ, tune that by FN tip. You just twist and push the top BN with the graphene untouched. Then the moire will be engineered. Of course, it's not real time, but each time you push it, you got a new twisting angle, and you do the experiment repeatedly. You collect all the data. You find that actually the peak can be well reproduced by pushing the top of the end, and the alignment of graphene is changed continuously. You got all these theories in agreement of experiment. So this is so far for today. I think we finished at 45 or 30.
Finished 12:15.
12:15. Okay, great. So it's the first section. I will change to the slides of the next one.
Okay, I need to a few minutes on the front. I need a few minutes to make it all works.
Let's see.
Yeah.